buffer. How would I make that buffer? Well, I'd use the Henderson-Hasselbalch equation, right? And I'd pick some, we can pick basically anything we like, but we can, for example, pick, let's say, acetic acid. Now, let's go to our table. Right? Remember this table of acid strengths. Okay. Just a moment. I have to go back. Where is that table? Did we miss it?
Yeah.
Yes. So here are the pKa values, right? So what you would typically do is you'd actually pick something, if you're a scientist, just for convenience, that's pretty close to the pH that you want. So if I take methanoic acid, right, its pKa is 3.75, okay, 3.75. All right, and then I go back to the Henderson-Hasselbalch equation, right, which is very elegant, and I plug in the values. So what I want is 3.5. So there is the equation. pH equals pKa plus log conjugate base over acid. So you see, what it enables me to do is it enables me to tweak the pH that I want. By the way, if the concentration of the acid and the base in my buffer is the same, the pH equals the pKa. Do you see that? Because if the concentration of the acid and the conjugate base is the same, it's going to be log 1, which is 0. So if you want to make a buffer system that has, it happens to have the same pH as some pKa of some weak acid, you can just make a buffer with equal concentrations of the acid and its conjugate base. In this case, I want a pH of 3.5. So it's very simple. All I'm going to do is I'm just going to plug in the values. pKa is 3.75 plus log, let's just call this log x, right? Because we want to find the ratio of the conjugate base to acid. So what is log x going to be? Minus 0.25. And then you can solve for x, and that is going to give you the ratio of the concentration. So you'd go into a laboratory, and you can basically make a buffer that has the correct ratio of the acid and its conjugate base to get the right pH. That's how you use the Henderson-Hasselbalch equation. Okay, and that's an example. You can solve for that. Basically, it's going to be 10 to the minus 0.25 will be x, right? So actually, let's just do that. 10 to the power of minus 0.25 equals x equals the constant equals this. So 10 to the power of minus 0.25 will be the ratio of the conjugate base to the acid. And if I then go into a laboratory and I make the concentration of the base, the concentration of the acid, such that their ratio is 10 to the power of minus 0.25, I'm going to end up with a buffer system that has a pH of 3.5 using this specific system. So this system would be the acid would be formic acid or methanoic acid, same thing, and this would be something like sodium formate. Right? So it's always the weak acid and its conjugate base as a salt. So that's the Henderson-Hasselbalch equation. I mean, there are limitations. Typically, there must be a certain ratio for it to be effective. Typically, the ratio should be between 0.1 and 10. Okay, the ratio of the conjugate base to acid. Then it tends to be an effective buffer. But yeah, I mean, that's just sort of a side note to this whole thing. And in your body, we have, of course, a buffer system as well. What is the buffer system? Carbonate, exactly. Carbonate, carbonic acid. And that works because we actually saw that earlier, also because it's amphoteric, remember? H2CO3 can behave as an acid. Well, it can give off a proton, and it forms HCO3 minus, which can either pick up a proton or give one away. So yes, the buffer system in biology is the carbonic acid carbonate system, which is also very effective. The last thing I want to talk about today is indicators and acid-base reactions, which I think you are all already familiar with because you did this for the pre-discussion, hopefully. And I mentioned earlier indicators, and I showed you the example of that cool indicator with the red beetroot. And so what are indicators? Well, the indicators are substances, again, that change color at different pHs. And the reason why they change color is because there's typically these organic compounds that get protonated. In other words, they pick up a proton at low pHs because there's a high concentration of H pluses, and that changes their chemical structure in a way that it changes their color. Because organic compounds, depending on their structure, can have beautiful colors, right? And if you protonate it, it somehow changes the structure and changes the overall color of the thing. And if there's a low concentration of H pluses, for example, at a basic pH, then it would not be protonated, it would have a different color. So that's sort of how it works. And you have a whole range of different acid-base indicators, which I show here, which change colors at different pH ranges, typically 2 pH units, right? So depending on what sort of situation you're working with, you would select a different indicator. The indicator that we would use if we want to see a color change between acid, basic, and neutral would, for example, be phenol red. Because you can see it changes its color. At yellow, it would be, at 6, which is acidic, it would be yellow. Neutral would be orange, and red would be basic, right? But you have other situations where you might be interested in a pH change at a much higher range. For example, alizarin yellow goes from yellow to violet around pH 11. Now this is again because all of these are different organic compounds which, depending on their structure, change or become a different color at a different pH, which has got to do with the chemistry of the actual indicator. You also have some indicators which change, like methyl violet, at very low pHs. You can see between 0 and 2, it changes color. So this has got to do with the chemistry, the organic structure of these indicators. Now, what we typically do is we would want to do so-called acid-base titration, which is where we try to determine the concentration of an acid or a base. Let's say we have a solution and it's an acid and we want to know its concentration. We would titrate that or react that with a known concentration of a base. Why? Because an acid plus a base forms a salt plus water. And we use a suitable indicator to do the experiment. Now when you do these so-called neutralization reactions, there's 4 important terms. The equivalence point, which is the point at which both the acid and the base have been consumed and neither is present in excess. The end point, which is the point at which the indicator changes, okay, which is kind of the same in a way as the equivalence point, but this is sort of the experimental fact where you see the color change. For example, you know, let's say from 6 to 8, if you see it changing orange, then that would be the end point of the experiment. The titrant is the known solution added to the unknown solution, and finally you get a titration curve, which I think most of you have encountered in the task. If you plot the pH as a function of volume of titrant being added to the thing. So this is sort of the experimental setup that you have. You have a burette, and you have at the bottom sort of so that's the titrant. And you add this very carefully. The burette is highly accurate, right? And you can, with 2 decimal places, actually record the volume required to, let's say, neutralize what's at the bottom. So if you know the volume and the concentration of what's in the burette, you know the number of moles. You don't know the concentration of the stuff at the bottom, but you can sort of do a calculation to figure it out using stoichiometric calculations. That's the principle behind this. And then you could get the concentration of, let's say, the acid or the base that's in the bottom, is what you're trying to do, right? So you know the concentration of this guy, you know the volume needed to do the reaction. Remember, there's an indicator in there. And if you know the concentration and you know the volume, you know the number of moles. You know the volume here because you add a very specific volume of the unknown concentration that you're trying to determine. But because they react in a one-to-one fashion typically, you can actually determine the concentration. That's the principle of an acid-base titration. It's an experimental thing, and you'd add an indicator here and very carefully do it until you see a color change. And this is, for example, a titration in a laboratory. Here you have before endpoint, so you're basically adding the titrant, you're swirling it around, doing it very carefully. At endpoint, in other words, when you see the color change, in other words, when the two have reacted completely with each other. For phenolphthalein, this is a specific indicator, for example, it would turn light pink. And if you add literally 1 drop more, it turns dark pink. And then you have got sort of overshot the titration. So this is sort of the experimental practicalities of doing an acid-base titration. Right, and the endpoint must match the equivalence points of the neutralization. The endpoint is the experimental thing. What you see, this is the endpoint, and the equivalence point is sort of that the two have just neutralized each other. Okay, so the ones, they basically mean the same thing, but the one is what you see and the other one is what's happening in the actual vessel. So here are some videos, and I think we've actually got enough time that we can actually watch this. So let's just see how this looks. I'm just going to select this and copy this. This is from YouTube. This is an acid-base titration. And let's have a look at how this looks. You unfortunately are not doing an acid-base titration in your practical, but let's just have a look at this, right? So this is what we're doing in the lab, guys. We're trying to determine the concentration of the stuff at the bottom. And so we don't know the concentration, but we know the volume. All right, so we take out we use a pipette for that, that's very accurate. To pipette 25, in this case, 25 cubic centimeters of HCl from our unknown solution into the conical flask. Remember, we want to determine the concentration of the stuff that's in here. And we very carefully, with the pipette, add it over. So we know the volume in here, okay? Now we add phenolphthalein. This happens to be a suitable indicator, okay? And in fact, phenolphthalein in acidic media is colorless. Now check this out. Now he adds basically the sodium hydroxide to the burette, knows the concentration of that solution, so that's a standard solution, and he adds it to the burette. And now he starts doing the titration. Watch what happens. It turns pink, but then the pink color disappears, right? So the moment that the base reacts with the acid, it turns pink, but then it goes away again because it's being neutralized by the acid. Phenolphthalein turns pink in a basic solution. And you keep adding this, so let's see what happens. Doing it very carefully, and it keeps...
Overshot.
Well, let's see.
I'm just kidding.
Let's see. But you must do it very slowly. Okay, that's exactly the right... Well, in fact, the way that he's holding the tap is not really correct, but okay. What's wrong with the way he's holding the tap? If you open a tap like that, you can pull it out, right? You've always got to hold it like this. Okay, but this isn't a practical course. This is just right. So we're still not at endpoint. We're still not at endpoint. Maybe now. No. See, this is something that you have to do very carefully. So this is a lot of fun to do actually. Now this is an example of a strong acid, strong base titration. Okay, we've reacted a strong acid with a strong base, and you can see that he's proceeding very, very cautiously at this stage. It still disappears. Okay, and now it looks like, well, I wouldn't say that that's the end point. I would say that he's gone a little bit over the end point, because the end point should be light pink. So he added maybe 1 drop too much. Now, the point is, he can record the volume of base that he's used by reading it off the burette. He knows the concentration, he knows the volume, so he can get the number of moles of base that reacted with all the acid. So because it's a one-to-one reaction, he knows the volume of the acid, he knows the number of moles, he can get the concentration. So that's what we're basically doing in a titration. Now that's an example, a very simple example of and a classic example of an acid-base, strong acid, strong base titration. This is what you would end up with if you were to plot the pH as a function of titrant. This is precisely what he was just doing, right? The pH varies very slowly in the beginning, and then it shoots up in a sort of a sigmoidal fashion. And that's why if you add just one drop too much, the pH can literally go from 4 to 10 with just a drop because of the sigmoidal shape associated with the acid-base titration. Because remember, we're dealing with logarithms, right? That's why. One drop is a lot if you're dealing with logarithms. So this is basically, in a strong acid, strong base titration, the equivalence point and the end point would have a pH of 7, okay? Now, this is basically an example of adding a certain volume with a certain concentration and plotting the pH. You can do that. Point is, you're going to end up with a pH of 7 regardless. If it's a strong acid, strong base titration, you're going to end up with a pH of 7. And this is just a very nice illustration to show that if you use different concentrations, right, as the titrant, you end up with basically 3 different sigmoidal shaped titration curves, but the equivalence point of all 3 is at 7, right? So strong acid, strong base titration always has an endpoint pH of 7, regardless. And you can then use the suitable indicator for that. Now, if we look at the titration curve of a weak acid with a strong base, let's say we do a titration of acetic acid with sodium hydroxide, where will the equivalence point be? Above or below 7? Weak acid, strong base. Sorry? Above 7. Why?
The base doesn't have much neutralized after the acid, so we have more base concentration than acid.
I think basically the simple way to think about it is like you have a strong acid and a weak base. A strong base and a weak acid. A weak acid would have a pH of, let's say, 3, and a strong base would have a pH of 14. What is the middle point of those two? It's about 9, 8 or 9. Right, so it kind of makes sense, doesn't it? If you start off with a weak acid, its pH would be not 0. Its pH would be like +3, let's say, and a strong base would have a pH of 14. The average of those two is certainly above 7. That's the way I think about it. It's a simple way of thinking about it. Strong acid, so weak acid, strong base has an equivalence point around 9. Okay, around 9. Okay. This is some stuff that I think you've probably, for the post-discussion today, looked into, I hope. Right? The equivalence point, the structure of this curve, and so on. This is just to show you what the approximate form is. Important is you have the so-called half equivalence point, which is simply half the volume required to reach the equivalence point. And at this stage of the game, in a weak acid, strong base titration, we call this the so-called buffer region. Now, you can also, of course, have it the other way around, where you do a titration of a strong acid with the weak base. So it's just now, what's in the bottom in the conical flask is just, instead of the acid, it's the base. Then, of course, as you add the acid, the pH is going to go down. You're also going to end up with a sigmoidal curve. In this case, it's a strong acid, weak base titration. Same thing holds. I'm now starting with a strong acid and a weak base. So the equivalence point is going to be below 7. Because a strong acid would be, let's say, pH 1. A weak base would be pH, let's say, 9. What's sort of the halfway mark of those two? Well, it would be around 5. So this is what you'd end up with for a strong acid, weak base titration.
On that one real quick, so 7 is right in the middle.
Correct.
So from 7 to 9, it would be weak. From 7 to 10, it would be a weak base. Like,
correct.
When do you decide what's weak and what's
Oh, that's a good question. I mean, I would say 7 to 11.
7 to 11 is
Yeah.
weak.
Yeah.
And then the opposite
Yeah,
way?
I'd say like 3. Anything with a pH between 3 and 7 would be considered a weak acid.
11 and 3.
Right, but this is sort of like, using some hand waving, but these are approximations. Now, that's it for today. I just want to finish with a summary of importance equations. Let's just revisit this. The definition of Ka and Kb, right? Remember, these are no different in essence than Kc. They're just specific for acids and bases. And remember, we dropped the water. That's very important. Remember, these guys give us a measure of the acid strength or the base strength. pKa is just negative log Ka. pKb is negative log Kb. We have this for convenience. pH is negative log H plus, right? It's a logarithmic scale. Can go to 14. Kw, the ion product of water, 10 to the minus 14, remember? 10 to the minus 7, 10 to the minus 7. And pH equals pKa plus log conjugate base of acid, the Henderson-Hasselbalch equation, which we derived, right? Which I expect you to be able to derive, because memorizing equations, especially memorizing the Henderson-Hasselbalch equation, is not something that I think is particularly instructive, but you can derive it. And here are the learning goals for today. I should have put them at the beginning, but why not put them at the end? Right, know the definition of the 3 bases with the base models, Arrhenius, Bronsted, and the Lewis, and be able to really not just, like a parrot, write down the definitions, but apply it and understand it. Is this a Lewis acid? Is this a Lewis base? Is this behaving as an Arrhenius acid? Why? How? Right. Being able to write down acid-base reactions, identify conjugate acids and bases, and write down equilibrium constants for the reactions, particularly Ka and Kb, right? Because we're talking about acids and bases. Calculate pH, Ka, Kb, and pKa. And remember this whole thing, this calculation example that we looked at, how to treat a strong acid